Okay, here we go. The normal curve, normal models. So first, before we get to the normal distribution, I want to just show something that is about distributions. I mean, what do we mean by a distribution? Before we start, classifying something as normal, then let's just come up with our own distribution. So just to give us some data to graph here, I'm going to ask you, try to think for a second, how many states or countries have you been in? Okay? And think for a second. And then I'm going to come around and ask you, okay? Like Matt, can you think? 26? Okay. And Kirsten? 11? Okay. And Vishal? 12? Okay. You mean more or less? Joby? I mean, you can count states as being different states, right? Josh? 17? Okay. States or countries? Mike? 17? About 17? Okay. Let's go back to Gabriel. How many? 8? Okay. Olivia? Say again? 48? Hey, you're breaking the curve here, okay? Panita? 14? Okay. Anna? 12? Okay. Lizzie, quiet please. Quiet please. I can't hear. Right? Yeah. 10? Go ahead. 15. Fair amount. Let's go. 13. And Lauren. 19? 19. Okay. And let's see. Count. 3? 3? Another 3. Okay. 10. And 11. That corner, Jason. 5. Okay. And 16. Okay. 15. Okay. And what's that? 50? Are we trying to set the record or something? Yeah, I don't think that's all the countries. 50. Okay, Darren. 5, and finally Jason. Jason, 20? Okay. So I'm going to make bins, what you would call in when you graph this kind of thing, bins, right? I'll make each bin is going to be a width of 5, right? So for the first one, it'll be 1 to 5. I'm going to have to spread it out because we've got such varied values. 6 to 10, right? Then we got 11 to 15, 16 to 20, 21 to 25, 26 to 20 to 30, 31 to 35, 36 to 40, hardly fits, 41 to 45, and then the last one is going to be the 46 to 50. So that's my x-axis. And then for each number here, I'm going to put an x above that bin number. So for 26, we'll go here as an x. 11 and 12 go here, so x, x. 3, 17, 17. 3, 17, 17. 8, 48. 8, got 1 all the way over here. 14, 12. 10, 15. 13, 19. 3, is that a 10? I think so. It doesn't really matter, but 3 and 10, I don't want to shortchange anybody. 3 and 10, 11 and 5. Oops, that shouldn't have gone there. Edit. Undo. 11 and 5. And 16 and 50, 16. Another one all the way over here. 5 and 20. 5 and 20. So, I mean, you could call that a frequency distribution. When you just plot a bunch of x's, you know, for the number of times that it occurs. And another thing you could do, which makes it even more recognizable, is you could like put a rectangle, a bar that goes above. That's the height of all those x's. And I imagine some of you have done diagrams like this before. What is it called? It's called a histogram. A histogram. So a histogram is specifically when what you've got on the x-axis here are numbers, right? They're numbers that could be put in order. And as opposed to, for example, if we were like counting how many people have each color of eye, like blue and brown, and how many colors are there? You know, then if that was what your categories were on the bottom, there's no reason that they'd be in order necessarily. You know, blue doesn't have to go before brown, right? You could switch the order. But 1 through 5 has got to go to the left of 6 through 10. So when you make a histogram, you should always make the rectangles, they should be touching each other, which kind of implies continuity of things, right? They have to go like that. But that's an example of a distribution, right? It's showing you the distribution of the number of states or countries that you all have visited. Okay, we might say that it's it looks like it's maybe it's unimodal, maybe you might say it's bimodal, because you know it goes down and then it goes back up again, something like that. Okay, so when you do a bar chart, it could be called a histogram. You know, histograms could look all kinds of different ways. These are just, you know, did a Google search of histograms, and I copied a few of them onto a slide. These are all histograms. They all have numeric x-axes, and the rectangles are touching because of that. You know, you'd probably say that this is unimodal, and that's unimodal, but maybe that one's bimodal. It's got 2 peaks in it. Okay. Now, this one here, that's pretty close to being a normal distribution, because normal distributions are unimodal and they're symmetric. And that one's not bad. I mean, it doesn't look like it's perfect, but a lot of times, you know, when you're doing real world stuff, it's never perfect. You know, you would look at that and say, that's close enough to perfect, and probably treat it like it's a normal distribution. But, you know, when you do a distribution like that, I mean, you're going to have like a finite number of values that go into it. And then you're going to have rectangles, discrete rectangles that represent that. Okay. A normal curve is when you actually, there's a mathematical equation which describes distributions that we call normal. But usually, normal distributions, not usually, they are unimodal and they're symmetric. And, you know, they can be the result of, generally like random processes. You get that kind of a thing. Like when I drive to school every day, it doesn't take me the exact same amount of time every time, right? It's usually, you know, between 20 and 25 minutes. Maybe if I did it like for the whole year and I recorded everyone, the mean would be 22 minutes. And then I would have a little bit less, that would be the highest point on the graph, and then I would have a little bit less at 21 and 23, and a little bit less at 20 and 18. It would fall away on either side like that. You know, but okay, so why does me driving to school, in what sense is that a random process? Because what are all the things that affect how long it takes me to get here? The lights you hit, the traffic, maybe the weather, yeah. It could be the route you take, yeah. If I don't specify that would change it.
Like outside things like schools and stuff?
It could be, or it could be like, you could say you run into an animal on the road, accidents, you know, maybe if you drive on 64, there's a, you know, the block there somewhere. So all those things can affect it. But overall, if I did this, if I measured this time after time after time, I would end up with my distribution would probably look like something like, actually without even drawing it, it would probably look something like that. Probably. Okay. So we can approximate what is a normal distribution with a mathematical curve, right? So you see this is the curve, and it's a model, right? It's not perfect, and the underlying data may not have been exact. You could see some of these rectangles are like overshooting the curve, and some of them are kind of undershooting the curve. But it's like a best fit line. That's what it is. And you can see that the shape of it is kind of like a bell. It's called a bell curve. Right? So I don't even remember. I cut off what this is. It says the counts of primes, but I don't even know where I got it from. There's one thing that's a mistake on this one, according to what I just told you, that because this is a numeric scale on the bottom, these rectangles really ought to be touching. So it's a bar chart if you just have like gaps in between, and that kind of implies you could just like move them around into different places. Right? But that is the normal curve, or you could say it's a model. So there's actually an equation for that. You don't have to write down this equation. We're not going to use it or anything like that. But it's a very precise curve here. And you can see that the f of x, it's not written just f of x, right? It's f of x, then it's got this vertical bar, which in math you read that as such that. And then it says mu and sigma squared. So basically, each normal curve is defined by its mean and its standard deviation. And if you know those, then you completely could draw and label your normal curve. So you look in the formula here. There's the sigma. It's got a pi in there. It's, it is exponential, but it's actually, and you would think because of the negative right there, it might be exponential decay. But because you're squaring that, it's not going to be like the typical exponential decay that looks like that. I mean, clearly it goes up and it goes down. Okay, now this is the x-axis, right? So if x equals the mean, that puts you right in the middle of the bell curve. So the value of x at that point is mu. So just if you plug in mu, what do you get? Mu minus mu is 0. So e to the 0 is 1, right? So in fact, then the value of the function is going to be whatever the value of this coefficient is right there. That's the height of the curve in the middle. Okay. Now, the area of the underneath the curve is 1. And it actually, it still has an asymptote here. There's no way you can make this function equal 0. So even though it looks like it's touching the axis, there's actually a tiny, tiny infinitesimal gap in between the bell curve and the x-axis. So it goes on forever to each side, but it's like that some little area underneath the curve is actually approaching 1 like an asymptote. The area under the curve is approaching 1. Okay, what's the other thing I want to tell you? So you can see that the standard deviation is important to the bell curve right here. Well, the standard deviation, so the mean always goes in the middle. That's the mean, mu. And then you go in standard deviations, like to the right, that's plus 1 sigma. And over here, that's minus 1 sigma. And if I go up to the curve, it's going to intersect maybe about right there. Not coming in very well. That's usually one standard deviation to the right or to the left should be about halfway down from the peak. It looks like it's not quite right on this one, like maybe it's not quite halfway down, but that should be like in the vertical sense about halfway down towards the x-axis. And then the other thing that's important about this is that if you notice the curve, it's concave upward over here and over here, right? But it's concave downward in the middle. So the point at which a graph changes from being concave in one direction and to the other direction is called the point of inflection. And that's exactly at that point right there. It's exactly one standard deviation to the right or to the left is where you start changing, drawing it like it's going like that and make it concave up on the sides. I mean, you could use those kinds of things to help you draw a better bell curve. I mean, in the end, it doesn't really matter. If you got to draw a bell curve, I don't know why I did that. Some people will just like go like this, you know, make a semicircle or something. Okay, fine. You know, as long as you do everything else right, it's okay. But it is supposed to be somewhat shaped like this. I mean, you could put that, if you go to y equals, you could put this equation in the calculator. You would just have to give it a value of sigma and of mu. And the rest of it you could put in there and then set your window. Set your window so that the maximum y value is this value right here. And you would get a very good bell curve out of that. So the thing about the bell curve, you can do a little calculus and figure out what's the area underneath the curve between the different standard deviations to the right and to the left. And they are actually fixed. It doesn't matter what the mean and the standard deviation are. You will always have 68.2% of the data will be in between one standard deviation to the left to one standard deviation to the right. And in between two standard deviations, left and right, you get 95%, 95.4. And in between -3 and +3 standard deviations, it's 99.7% of the area under the curve is between those two. So what percent of the data is not between -3 and +3? Yeah, 0.3%, right? If this is 99.7%, there's 0.3 that's not in there. And since it's symmetric, you would know that actually half of that, 0.15 must be to the left of 3 standard deviations over here, and 0.15 would have to be to the right of it. This is called the empirical rule, right? Sometimes it's referred to as the empirical rule. Most of the time it is. One book that I taught out of, they called it the 68, 95, 99.7 rule, which is really clever. So if you memorize that, then you kind of know the percentages right there. And you know, then usually we weren't saying like 68.2 and 95.4. We were just saying 68 and 95. Okay, so when we do calculations with the normal curve, a lot of the questions are really just to do about this one diagram right here. There are questions that you can answer by just knowing these percentages, right? And you notice that the percentages, besides the 68, 95, 99.7, if you just divide everything by 2, then you get these smaller, you know, 34.1, 13.6, 2.15. So if you knew, if that's all you knew, you could answer most of the questions. So here we can do a probability. The P is for probability. What is the probability that the X is in between this mu minus 2 sigma, means it's in between this point and mu, right? So it's in this region. So a random value taken from this normal distribution, what is the probability that it comes from this interval? And you would add up those two, right? And what would that be? $47.7? Okay. So that has to be these two right there, right? You add those up. And since it's a probability, you know, you probably should say 0.477. Probabilities are usually between 0 and 1. I think when in the book, when they do it like this, they want the decimal value. A lot of the questions in my presentation here today, it actually asks for the percent, so you can just use the percent. Okay, let's try this one. Try to do those 4. Use that same bell curve and see if you could find the probability that x is less than or equal to mu. Again, what does mu represent? The mean, right? What's the probability that x is greater than or equal to the mean? Right? What's the probability that mu is between the mean and 2 standard deviations to the right? See if you could peel the percentages off of that. So on the first one, if this is a symmetric, right, shape, and the mean is like right in the middle, then what is the probability that you would be less than the mean? 50%, right? What's the probability you're more than the mean? 50%, right? So as a probability, we might put 0.5 and 0.5. Okay, on the last slide, we did the probability of being between 2 standard deviations to the left and the mean, right? That was 0.477. So this one is saying what's the probability of being between the mean and 2 to the right? Same thing, right? You're adding up the same numbers. Easy stuff. Okay, what about the last one? In greater than or equal to the mean plus 1 sigma. What did you say? 15.9%. And so how did he come up with 15.9? Is that the sum of these two here? No, not quite, because remember that these are only telling you out to 3 standard deviations to the right. This thing is saying what is the probability of being continuously, like all the way to the right. So that includes that little bit that's to the right of 3 standard deviations. Well, what did we just say? What is the probability of being from here to the right, from the mean? And that's 50%. And then what is this little piece that's missing? 34.1. So if you can subtract that, that's where you get 15.9. So for here, we'd say 0.159. That is the probability. Okay, so I'm going to do a problem here to show you how it's actually probably, I think there's some teachers that still teach this as the main way you would do these kind of calculations. But we won't. After we show how you do it this way, I'll show you how to do it with the calculator. Because really it's something we should be doing on the calculator these days. So here you go. Scientists conducted aerial surveys of a seal sanctuary and record the number X of seals that they observed during each survey. The numbers of seals observed were normally distributed with a mean of 73 and a standard deviation of 14.1 seals. Find the probability that at most 50 seals were observed during the survey. So draw and label a normal curve. which I've cheated. I copied the same graphic from before. But sometimes it's not really necessary to draw the normal curve, but sometimes it really is. Generally speaking, like when you get to AP Stats, let's say you take AP Stats, you want to be drawing yourself a normal curve and labeling it because it'll help you get the calculation right. So in this case, we should label the middle with the mean. We just said the mean is 73. And the standard deviation is 14.1. So that would make one standard deviation to the right. I should add 73 plus 14.1. 87.1. Okay, 2 standard deviations. Add another 14.1. Right? 3 standard deviations. Add another 14.1. Okay, then you go to the other side. Right? 14.1, 73 minus 14.1 is 58.9. And minus 14.1 again, 44.8. And minus that again, 30.7. So we are being asked to find the probability that they observed 50 or that at most 50 were observed. So 50 is like in between those standard deviations. Maybe it's a little closer to there. So essentially what they're asking us to do is find the area underneath the curve that goes infinitely to the left all the way up until you get to 50. Okay. So this is the process. First, you calculate the z-score for 50. Okay, that's why we did z-scores. Remember, z-score is the data value minus the mean divided by the standard deviation. In this case, the data value is 50. The mean was 73. And the standard deviation was 14.1. So you calculate it. And Kristen, what'd you get? Negative 1.6. Okay, that's the first step. So calculate a z-score. Now I'm gonna skip over a slide and go back to it in a second. So with that negative 1.6, then you get z-tables. And they actually give you z-tables when you take the SOL. They give you the formula sheet and they give you the z-tables. So you would look up in the z-tables for negative 1.6, right? There's z, negative 1.6, right? Negative 1.60 would be right there. Right? If I had negative 1.61, it would be there. I think it was actually like negative 1.63. So we could be a little more fine and like take it from this column. But if we just say 1.6, it's going to be 0.0548. So on a z-table, what they're reading off, that's the area under the curve to the left of that z value. So just like we just showed over here, the 0.0548, right? That is, the area under the curve is 0.0548. And what is the percent then? 5.48%. So what's the probability that at most 50, I mean, it's about 1 out of 20. You know, meaning that 19 out of 20 times you would have seen something more than just that. That would have been unusual to only see that many. Now, if you label your curve, you know, with the mean and the standard deviations like we did before, and that's 50, that's a normal curve. If you label it instead with the mean of 0, the standard deviation is 1, and then we already calculated the z-score, it was negative 1.6, right? That's called the standard normal curve, right? Standard normal curve. So that's where the mean is 0, the standard deviation is 1. Okay, now, so like I said, the z-score, if you look it up in the z-table, right, and you draw yourself a normal curve, you labeled it all, the 50 was right there, and we calculated that the probability, or the percentage, that it would be in that area right there was 5.48%. Well, what if the question was, what's the probability that you saw at least 50 seals? Right? Then you wouldn't be looking for the area to the left, you'd be looking for the area to the right. So you would want that area right there. But that's not in the table. When you do the lookups, it's not telling you the area to the right, it's only telling you the area to the left. So what do you have to do? You subtract 1 minus the area to the left, right? 0.0548. So that's all part of using the z-tables. There's a lot of, what if I wanted in between two values from 50 to 70, right? You'd have to do a lot of subtraction. First you'd find the area to the left of this one, then you'd find the area to the left of this one, then you'd have to subtract. And you'd have just the area in between those two. But we're not going to end up doing that because, in fact, your calculator does normal distributions for you, right? And it's on a button that we've used a couple times already, vars. Except for we're not going to use vars, we're going to use second vars. So you should get out the calculator and try this, right? Second vars, and you see this menu right here, right? Now, we only use normal CDF, which is 2, right? We never use 1. Even in AP Stats, we never used 1. The only reason you'd use 1 is if you wanted to actually graph the normal curve. It's only telling you the height of the curve at any one point. We don't want that. We want to know the area underneath the curve between a range of values. So that's normal CDF is normal cumulative distribution function. So you go second vars 2, and then it brings up this menu right here. Now, when you're finding the area under the normal curve, let's say that I was finding the area between these two places, right? Then the lower means the x value, which is to the left of the shaded area. The upper is the x value, which is to the right of the shaded area. Now, for the problem that we just did, in fact, our area, it ended at 50, but it went infinitely to the left. So we had a value for the upper, that was 50. But actually on the left, we didn't have a value. It goes on forever. So what you do is just put in a really, really small number, something that's way less than, that there's any appreciable area underneath the curve. Usually your calculator is going to automatically have put -1 E99, which is -1 times 10 to the 99th, which is very much to the left. We don't have to worry about it. And then you're going to put in we know what that symbol mu means, right? That's the mean. So you're going to put in the mean, and you're going to put in the standard deviation. Let me do it here, because I don't think I have it on the next slide. So let me shrink this and put up the calculator. I'm too busy. So second vars 2, and I already had something in there. So let's see, 7350. I'm just going to put in 0, 50, 73. 14.1. Right. Okay. Now, if you have a calculator at home, which is 83, or if it's an 84 that hasn't had its operating system upgraded, then when you go second bars 2, it's just going to bring up parentheses. It's going to say normal CDF left parenthesis blank. And then you've got to remember what values go in there, right? If you have the updated operating system, it actually prompts you for the values, so you don't have to remember that. So that's definitely something you want to go into the SOL having, well, you will, because we'll be using these calculators on the SOL. But if you're doing this at home, that's what it's asking for, separated by commas. You put them in. Like I said, before this, we just had to remember it, but now we don't. So then you hit enter, and it comes with the percent. Like I said, I think when we did the z-score, it was actually negative 1.63. So we got a 0.0514. If I go back again, yeah, negative 1.63, okay, 0.0516. We're getting closer anyways. Okay, so if you, where's this? So if there's no lower bound, like the one we just did, I mean, it stops here and you're trying to add up all this area but goes on infinitely, then for the lower bound, you just put something that's much, much less than the mean. It doesn't have to be negative 1E99. I mean, I've just put in 0, and that was pretty good. If you have on the opposite, if it goes like, the lower bound, but it goes infinitely to the right, then you're going to put in some really big number above the mean, right? But sometimes they give you the left and the right, the lower and the upper, but they don't always, so you just have to do that. Now remember the area under the curve is 1. Okay, let's try the next. So these are the typical kind of questions that you can get. 2,000 freshmen at State University took a biology test. The scores were distributed normally with a mean of 70 and a standard deviation of 5. Label the mean and 3 standard deviations from the mean. So you've got to write in the 70 and then 3 standard deviations, 75, 80, 85, 65, 60, 55. Okay, next. What percentage of scores are in between 65 and 70? So between 65 and 70 is actually here. No, at 65 and 75. Well, these are like 65 and 75 are whole standard deviations away from the mean. So we can just do this with the empirical rule. What percent of the data is in between 1 standard deviation to the left and 1 standard deviation to the right? 68%. All right, let's change colors. Okay, what percentage of the scores is in between 60 and 70? I mean, you could just go back and look at it's the same one we did twice already, right? That's well, you can add them up from that graph. The other thing you say, what would it be if I went from 60 to 80? That would be from 2 standard deviations to the left and 2 standard deviations to the right. What percent of the data is in that range? Right. Plus or minus 2 standard deviations is 95%. Right. So how much is in half of that if you just go 60 to 70? Well, that would be 95 divided by 2, which is 47.5. Okay, change colors again. Right. What percent of the scores are between 60 and 85? So from 60 to 85. How could we come up with that? I mean, how much is in between 60 and 80? We said 95%, right? So from 60 to 80 would have been 95 from here to here. And then how much is it from here to here? 99.7, right? So if I do the difference, it's 99.7 minus 95. Yeah, that would be 4.7, but half of that would be on one side and half of it would be on the other side, right? So what is 4.7 divided by 2? 2.35. So we'd have to say that it's the 95% plus another 2.35%. That's this one right here, 2.35, which makes 97.35. And those are all percents. So if you get asked the question and they're asking you about whole standard deviations from the mean, then you can use the empirical rule and answer all those questions. Now, sometimes they're going to ask you about a percent, like they have already. Sometimes they're going to ask you about how many, not just a percent, meaning that the distribution was made up of how many different individuals, and they want to know how many of the individuals landed in that region. So the way you do that is first you calculate the probability to be in that region, and then you multiply by the total. So when they ask for the number of, the first thing you got to look at, okay, where's the total? They must have given us a total number. So we'll see that on the next slide. So let me label this one again. It's the same distribution. So 70, I need to change colors. All right, I'm going to change it orange. 70, 75, 80, 85, 65, 60, 55. All right, so the first question, what percentage of the scores are less than 63? Okay, well, let's see. 63 would be right there. So go to your calculator. Second bars, 2. Okay, so this area goes on forever. So you need to put a number which is significantly less than 70. You know, at 55, which is 3 standard deviations away, there's only 0.15% of the area which is to the left. So I mean, if you put in 0, like I've got a 0, that's how many standard deviations below the mean? 14. So I think you're pretty safe. Yeah, if I can, I do. Okay, so I put in a 0. Okay, now it's ending at 63. That's the right end of the interval. So I put in 63. Okay, for the mean is 70. And the standard deviation is 5. Right? So now I hit enter. And again, there's the normal CDF. 0.0807, so about 8.1%. Okay, what percentage of the scores are greater than 79? Okay, let's change color. 79 would put it right there. It's definitely not a whole number of standard deviations away. Right? So now, second bars 2. The lower I know, that's 79. The upper is the thing that I've got to put something that's way greater than that. I'm going to put in 200. You know, if you don't think that's enough, then make it 2,000. You know, it doesn't matter. And then we use the same mean, the same standard deviation, and enter 0.0359. So how about 3.6%? Okay, now the next two questions, they're not asking for a percent. They're asking for approximately how many students scored between these two values. Well, again, they had, right away I'm going to look up at the top and say, okay, well, what's the total number of students? 2,000. Okay, so let's try this. Blue. No, I already did blue. How about red? Okay, so go second, bars. The lower is 66, second var is 2. The lower is 66, the upper is 73. The mean is 70, the standard deviation is 5. Okay, so the decimal that I'm reading off here is like 0.514, right? 0.514. But I need to multiply that times 2,000 to get the number of students. So right away just say times 2,000. And it looks like 1027.7. So let's round it to the nearest student, 1028. Okay, how many students scored between 58 and 62? Second, bars 2. 58, 62, enter, 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 enter. It looks like 0.466. So that I need to change colors again. 0.466 times 2,000. $93.2 will round to the nearest student, 93. So be aware if they're asking you for the students, the number of students, or the percents, or the probabilities, you know, slightly different questions. Okay. Keep doing that. Okay. So the truth is that you don't have to remember the empirical rule if you can just put it in the calculator anyways. Like now, I'm going to label this as 70, 75. This is the same data, 80, 85, 65, 60, 55. So what percent of the data is less than 55? Well, 55 is one of those whole standard deviations from the mean. So you could say, well, let's just use the empirical rule. But you probably have more trouble remembering the empirical rule than just put it in the calculator. Right? This is going to be all the area under the curve to the left of 55. So second var is 2, and I'll go 0, right, Kirsten, to 55, 70, and 5. Boom, 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 boom. And 0.001. 0.00134. So as a percent, that would be 0.13%. Okay, let's check. Percentage of scores greater than 80. Okay, again, 80 is definitely one of those whole standard deviations, but you could still use a calculator for it. Second, bars, 2. 80 is the lower. I'll put 200 as the higher. 70 and 5. 0.0227, so 2.3%. Okay, now, here's another how many. How many biology students were between 60 and 70? Second, vars, 2. 60, 70, 70 and 5. Now remember, that's not the number that I want. Now I've got to multiply by 2,000 times 2,000. 954.5, a little bit less, so 954. And how many were between 55 and 60? Second, bars, 2. 55 and 60. .0214 times 1,000, or sorry, 2,000. 42.8, call it 43. Now, one more thing. So the one last thing to tell you. So let's say the question is really about those standard percentages. Okay, well, you can calculate the standard percentages anytime you want. For example, if I want to know what is the percent of the data which is in between one standard deviation to the left and to the right, then do this. Second, bars, 2. And I'm going to say -1, +1, use a mean of 0, this is a standard normal curve, and a standard deviation of 1. So if the mean is 0 and the standard deviation is 1, we're going from -1 to +1. This should be the 68%. So let's see what we get. So 0.6826. There's the first number. Okay, what's the percent in between plus or minus 2 standard deviations? Okay, second, bars, 2. -2, 2, and 0 and 1. 0.9544. There's your 95%. And then the last one, second, bars, 2. All right, -3 to +3. 0.997. There's your 99.7%. So those percentages are never far away if you need them. Okay, that's it. That is everything. That is homework